Hey, what's up, guys? This is Chung. So today, another Codeforces problem. Uh, Sereja and brackets. Okay. Sereja has a bracket sequence strings here, right, from S1 to Sn, and only consisting of the left parenthesis and the right parenthesis. And we need to answer M queries, right? And each query is a range, basically from left to right. And the answer of each query is the maximum correct bracket, right? Subsequence. So subsequent, right? So it doesn't have to be a continuous like a string. It can be skipped. And here are the inputs, right? So the length of the string is 10 to the power of 6. And the second line is the queries, and the query is like 10 to the power of 5, right? Mm, So okay, so to solve this problem, so first thing first, right? Let's. I think most of you know what's the definition of the correct bracket? It means that it has to be a pair, right? So which means that if there's like a left parenthesis, there has to be a right one, right? And this one is also like valid, and this is also valid, right? But this one is not because this cannot be formed as a pair. So and it asks us to find the subsequence, right? So it can be skipped. So the most naive way or the brute force way is what? So for each of the queries, right, we just loop through from the left to right, and then we try to find all the matched pairs, right? But since we need to do a subsequence, right? So the brute force way is what? We can use like a stack. So for example, if we have like if we have like this one, right? So this one. Then we have this one, this one, this one, this one. Let's say the range is this one. So what's going to be the value here, right? So we are having like two pairs basically, right? So this is the pair, one pair, and this is the second one. So basically the answer should be 4. So by using a stack, so we can just so every time when we have like the left parentheses, right, we just push into the stack. And so we have a stack here, right? So the first one is the left parenthesis, and then whenever we see like a right parenthesis, we check the top one of the stack. If the top one is a left parenthesis, then we can pop the left out, and then we can increase the answer by 2. Okay, right? Because for example, this one, right? We have another one. So the second parenthesis, we just see okay. So the top one is the left one, so we just we just remove that, right? So and the answer will become 2. And then if the next one is still a right bracket, but there's nothing there, so we just push it inside. And then the next one is a left, we also push it inside. And then the next one is a right, and the top one is also a left one, so we can just remove this one, right? That's why we have another 2 here. This one again, there's no match, and this one is no match, right? So after processing this using the stack, we can get our answer for this query. But obviously, this solution is like a O(n) square. It's not. Actually it's m times n, right? So for m queries, each of the range, right? So the range is it's also also can be up to 10 to the power of 6. That's why this solution will TLE, will timeout. So it asks us, and then we need to find like a better data structure to solve this problem. So obviously our solution, our approach is we're trying to, since the m cannot be reduced, right? We regardless we need to query m times. Then our solution is we try to find a log n time, right, solution instead of O(n) solution. So for log n solution, what do we have? We have binary search, and we have segment tree, right? But for binary search, obviously this problem cannot be solved with binary search. So that's why we need to use a segment tree. Okay. But for the segment tree, but how will the segment tree help us solve this problem, right? Hmm. Let's try to draw some examples here. Okay. So some of you know that, right? So what is a segment tree? A segment tree is like, for example, we have like this. A segment tree is a tree, right? That the root node is the total range. Let's say, for example, we have in our example we have like this is 12 uh, brackets. So that's why we have 0 to 11. That's going to be the total range of the first node, right? Of the root node, and then we just split this one into two parts, right? Sorry. And we split this one into two parts. This one has like maybe 0 to 5, right? And this one have like 6 to 11, okay? Right? And then we continue until we have reached the leaf node, right? So here we have 0 to 2. Here we have 3 to 5, right? So which means that the segment tree, the node represents the total, the sum of the current range, and the segment tree, the value, the property of each node. First is the range. Second one is the some summarized value. Depending on different problems, it could be different structure, but the range has to be there. Okay, and so in speaking of segment tree, this is a traditional segment tree. There's also like a variation of segment tree called like a binary index tree, right? Or Fenwick tree. Uh, so the reason we don't use that one is because for the Fenwick tree, the it's usually used to query the count. So the count of each index. If we only need to know like the count for each of the index or the node, and then we just need and then we will just query the summary of the count, and then we can use the Fenwick tree. But for this problem, we don't care about the count for each of the node. We need to know the pairs, right? Basically, so the value for each node is going to be the pair from 0 to 5, right? The pair of the brackets from the 0 to 5 or from 0 to 1, so that we can use this one to solve our problem. And now let's go back to the problem, right? Assuming we have this segment tree, and how can we utilize this segment tree to help us solve the problem? Mm, as you guys can see, so the idea of segment tree is that by splitting a range into two parts, and then we just summarize some parts to into a parent node. And then let's try this. Let's say we have like a left string and a right string. So for the left string, right? For the left, we have this one. Let's say we're just drawing some brackets here. Okay. So let's say this is the left string, and this we have a right one. The right one is what? It's like this one. Mm, yeah. Let's say this is the right string. So with this kind of two substrings, basically, so the left plus right, which will be the parent, is going to be the answer. Assuming we have the answer for left and right, how can we get the answer of the parent node? Then probably for this one, we have to maybe analyze the sum of the properties or sum of the result from the left and right, and then we'll try to see that what kind of properties we need to put into each node so that given the left and right, we can get the answer for this parent, right? So what kind of properties we have here? So here we have two matched pair, right? that's going to be the 2. Here we have one matched pair, right? And here we have a parent, right? So with this left and right, what's the answer for the parent node? Of course, so it's 3, right? And then plus something. Plus what? Plus, see, so we have like a matched 2 pairs, and then we have like 3 unmatched left bracket, and then we have 1 unmatched right bracket. So what does it mean? It means that, so the answer for the parent node should be 3 plus 1 equals to 4, right? Because this one of the 3 left brackets can be matched with this one, right? And so I think we have already seen all the properties we need. So besides the current the paired bracket, we also need to have like another like the unpaired left parenthesis, and then the right, and also the unpaired right parenthesis. Because here, so the answer for this node is 2, right? And then so I'm going to use a left parenthesis. So this one denotes to the unpaired, right? The unpaired left parenthesis. So this one is 3, and this one, so the right unpaired parenthesis 0. So similarly for the right node, right? So we have the left unpaired parenthesis 0, and the right unpaired parenthesis is 1. So as you guys can see, right? So to get to the parent values, we need to do what? We need to do a left answer 2 plus 1 plus the minimum of the left parenthesis and the right parenthesis. So the left node, left parenthesis, and then the right nodes. So basically we have a left answer, right, plus right answer, right? So this is 2 part. And then we also add like the minimum of what? Of the left LP, right? And then the right, the RP. So that's how we get the answer for the parent, which is 4. Now, since this is like a recursive function, right? So besides the answers, we also need to populate the left parentheses and the unmatched left parentheses and unmatched right parentheses for the parent node. So what's going to be that, right? So that one is pretty, I think it's also straightforward. Let's say we have a matched, right? So let's say the matched is this one, a match, right? So let's say the match is equal to this minimum, right? That's going to be the matched bracket. So the parent's left unmatched left parenthesis is going to be the left dot LP plus right dot LP minus match, because we have to summarize all the unmatched left parentheses from both the left and right, from the left and right child nodes, and then we subtract the matched one, right? So that's going to be the remaining of the unmatched left parentheses, similar for the right one. So it's going to be the left dot RP plus R dot RP minus match. That's how we can use the child values to populate the parent value, right? And given this one, so and then given like a range, right? So we have a left and a right. So let's say we have a left and right range. We have some parentheses here. we can just use the after populating. Okay, so after populating this, build this segment tree here, we have all the values, right? We have all the answers and left LP and RP stored on each of the node here. And then once then we have like a queries from left to right, we can just basically we will split this this one into different segments. Okay, split this one into different segments, and until we have find an answer, we find the answer for the find some answers from each of the node, and then we're gonna stitch those nodes answer together to get our final answer. Mm, yeah, so I'll give you like a more concrete examples maybe. So um, so we have 0 to 11, right? So that's going to be the first one. Then we have 0 to 5. Here we have 6 to 11. Then here the next one is 0 to 2, 3 to 5, and then we have 0 to 1, right? And then we have 2, here 0 and 1. Here we have 3 to 4, 5, here 3, and 4. So for segment tree, all the leaf nodes are the actual elements. And so to populate this one, and what's our answer? What's the so we have this one. Okay. Yeah. So this is the input string, right? So the first one is a left. So whenever we reach a leaf node, which means that the left and right are the same, right? And then we can just populate the left and right because on a leaf node, for example, if at 0, we're at here, right? So 0, 1 is the left parenthesis. So what's the value for the 0 nodes? So the answer, obviously, all the leaf nodes has a value. Answer will be 0 because there's no pair if there's only one parenthesis. And then the left parenthesis for the 0 is 1, right? Because it's a left parenthesis, and the RP is 0. So for 1, what's going to be the answer? So we have like we have the answer also, right, equals to 0. The LP is 0 in this case, right? And the RP is 1. So for 2, 2 is what? 2 is like also like a 0. And the LP is what? LP is 0 and RP is 1. So now when we after populating these two nodes here, right? And when we populate this the parent node, which is 0 to 1, the value is going to be what? We have like so the LP, the minimum LP and the minimum of RP, which is 1. That's why the value of 0 for this one is going to be 1, 0, and 0. Right, so the 1, 0, 0, and then we'll go back to 2 here, right? We go back to 2 to build this 2 here. So for 2 is 1, 0, and 1. Because from 0 to 2, we have one paired, and then we have one remaining unpaired right parenthesis, and so on and so forth. That's how we build this like this like this tree here, right? And now let's see if we want to query. You want to query the query is gonna be the what? Let's see we have uh let's see the query is 2 to 5. How about that? Yeah. So let's try to see how can we solve this problem given like a query. So we have 2 to 5, and then first we'll go to the we'll go to the left and right, right? But so 0 to 5, right? It's not it doesn't completely include 2 to 5, right? It's a partial match because from 0 to 2 it's somewhere else. That's why we're going here, right? And then we're going here. But for 6 to 11, there's a completely no match, right? Because 6 is greater than 5. That's why we can return what? We can return 0. We'll return like 0, 0, 0. This will help us to simplify the code. So return 0, 0, 0, we return a node, but this node has like 3 zeros as its property, which means that there are like 0 answers, 0 left parentheses, and 0 right parentheses. And then for 0 to 5, right, we are like, it's since it's a partial, since it's a partial split, right, then we'll go to the left and and right. Yeah, so we'll go to left and right, and then we'll go here, and we'll come here. Mm, yeah. So now, for let's take a look at the right part. So the algorithm for the segment tree is that whenever there's like completely include, right, which means that if you see, so now the query includes everything for the current node because 3, 5 is within the range of 2 to 5, right? This is 2 to 5, and this is 3 to 5. 3 to 5 is completely within the range of 2 to 5. For that, in that case, we will simply return the node, the current node. And on the left side, right? So 0 to 2, it's still like a partial match, right? Because the 0 to 1 is not within this range. So that's why we have to continue going to the left and going to the right. Now the 2 is a complete match because 2 is within the range of the query. That's why we just return the value of 2. And then for the 0 to from 0 to 1, it's again, right, it's a no match. It's a completely no match. That's why for 0 to 1 we'll return a 0, 0, 0, 0, 0, 0 back here. And now see, so what are the return nodes in this case? Only this 2 and 3 to 5. And that's exactly our query range, which is 2 to 5. Right? Basically, as you guys can see now, we are splitting this 2 to 5 into two segments. The first one is 2, the second one is 3 to 5, based on how we build the node here. And this will give us like a log n time to solve this problem. Oh, by the way, so once return from toChild here, we'll apply the same merge uh, algorithm. Basically, we find the match, right? We find the match, and then we also use this same thing, the match, to calculate the remaining left and the right parentheses, and then in the end, we just return to the root nodes, and this will give us the final answer. Cool. I think that's everything I want to talk about for this algorithm. I think we can start coding. Yeah. Mm, cool. Let's see. So to code these things, so first we need to allocate the size of segment tree, and the size of this string is 10 to the power of 6, and then we will allocate this actually 4 times n. 4 times n. So the reason being is that, maybe I'll try to explain a little bit about this. Why, let's say given like n, given like a n array, So the biggest the biggest segment tree array we need is 4 times n. And why is that? Because like I said, the node, the leaf nodes are the elements, right? So considering we have like complete binary tree, if there's a complete binary tree, so we have this one, right? And let's say the leaf nodes are the nodes, right? So we have we have 8. So when n is equal to 8, so how many total nodes we have here in this tree? We have 2 times n minus 1, right? Because that's, I think it's pretty easy to prove, right? That's going to be the total number of the nodes in this complete tree, complete binary tree. And that's the case for complete tree. In that case, actually we only need two n nodes, right? But not every time the n is a power of 2, which means that not every time the n is this will form a complete binary tree. Let's say if n is something else. Let's say n is like it's 10, right? So if n is 10, this one will not be a complete binary tree. And since we're calculating since we're using the parent node to find the child node, and the algorithm is let's say the parent node is I, right? And the left child node is what? Is 2 times I, and the right child node is 2 times I plus 1. Okay, assuming the n is not a power of 2, and if we only allocate 2n nodes here, then for some I, when we try to find the left or child node, it could be out of the boundaries because um, because it will not form a complete binary tree. So the solution for this one is that we're always assuming that it's a complete binary tree, so that we're sure that the 2 times I and 2 times I plus 1 is always within the range. So how can we do that? Basically, we just add another layer. We not another layer uh, of the current one, which means that we do another 2 times 2 2n to the total array, right? Because with a complete binary tree, if we add like another layer here, so what's going to be the amount of the last layer? It's going to be the previous layer times 2, right? And that's why we use like 4n instead of 2n to hold all the elements in the not all the nodes in the segment tree. If you don't uh, if you're not buying this proof here, you can just remember, whenever you do like allocate a space, always do a 4n. Cool. So that's that. All right. So and the next one is we have a m to read, and then we have a string to read, right? So that's the two things we need to read here. And cool. So first, let's read the string in. And string, that's string. And then for the size, right, we have an n here equals to string dot size. And the first is which will build this segment tree. So to build a segment tree, we need 3 parameters. The first one is the left, right? That's the range, the left range, and then we have a right range, which is n minus 1, and then we have an index. Index is, the index for the node. We start from 1. You could from 0. You could start from 0. It's okay. It's just that if you start from 0, let's say we have this one. So this is the tree node, right? Assuming we have a complete tree. If we start from 1 here, so let's say the root node is 1. So the left child is what? It's 2, 3, 4, 5, 6, 7. Okay, so that we can use the left child is a 2 to the 2 times I, and the right child is 2 times I plus 1. Right, so that's how we get this formula here. But if we start from 0, right, let's see if we start from 0. So what's gonna so this is 1, 2, 3, 4, 5, 6. Right, if you start from 0, then the formula will becomes to 2 times I plus 1, and then 2 times I plus 2. So that's the only difference. You can choose either way, right? But I'm using 1 here. That's why I'm going to use this one, right? Okay, so let's implement this build function first. The first we have a build. So the build, we're trying to build the range for the current node, right? So the current node, we have a left, and then we have a right, and then we have an index, right? So I'll use I as an index. So, and if the base case, right? So since the build is going to be a recursive call, right? So if the L is equal to right, then we'll just populate the node O. So before doing that, we also need to create like a object for the node. So I'm going to have like answer dot lp left parenthesis not matched, right parenthesis not matched. Then we have a tree, right, of max n. Okay. Did I? What? Okay. Weird. Weird. Uh, yeah. So when left is equal to right, and when it means that it's a leaf node, we can simply populate the tree node, right? So it's going to be a tree of the index of I equals to what? Equals to the first one is the answer, is always 0, and the left parenthesis is the actually the string of L, right? If the current one is equal to left parenthesis, and the right the RP is the if the current one is equal to the right parenthesis. Okay, that's how we populate the leaf node. It's pretty straightforward, right? And then if it's a not leaf node, right, we're gonna split this node into two parts. So first we're gonna have a middle equals to the L plus right divided by 2. And then like I said, for the left child, right, so we have a left child equals to what? The 2 times I, right? And then we have a right child equals to 2 times I plus 1. This is the tree node, right? The node index for the left child and the right child. And then we just recursively call the build, right? So since we split into two parts, we have a left dot middle, okay? And then we're giving so the left index is going to be LC, right? And then we also build the right node subtree, the middle plus 1 dot R dot RC, right? So that's that. And after this one, right, after building basically we're building this tree from bottom up, and after building the child node, we need to merge so that we can build the current node, right? And so I'm going to do a basically tree of current I equals to I'm going to create a merge function to merge the left child and the right child. So to merge that, it's gonna return like a node, right? So we have a node of L, right, and then node of right. So we have a node of return the node, and then we have a match, right? So we do the match, and this match is going to be the minimum of left dot LP and then the right of RP. And then for the return dot answer equals to the left dot answer plus right dot answer plus the match, right? And then for the parent nodes LP is going to be the child nodes LP plus, right, then minus the match. Similarly for the right unmatched the right parentheses, right? Yep. And then we just return the return here. That's how we do the merge from the two child nodes. So and yeah, and that's it. That's how we build this build this segment tree. Now we can utilize this one to do our query, right? So okay, after building the segment tree, we read the m queries. So it's going to be m, and then we do a while this m, this one. We have int dot since we already have like the L and L and R as a parameter name, so for this queries, maybe I'll just use a start and end to store the query value. Okay, that's that. And then I do a s minus minus e minus minus. Yeah, because this one is like it's a one base, right? But the the array here, the array we're building is like it's zero based. Yeah, because when we build this tree here, we start from zero, we end with n minus one, which means that we're building it based on a zero based range. That's why the when we try to query this segment tree, we should use the same base, right? Which means that it has to be a zero based. And then here, I'm going to have a node here. I'm assuming we have a queries here, right? Query algorithm. So the first one is the range, uh, the range of the query. So at the beginning, it's going to be n to n 0 to n minus 1, and then the of course our query range is going to be a s e, and also there's one index of the tree. Okay. So now let's implement this query function. So like I said, query function is going to return like a node here, and this node will give us the final answer because because in the end we simply do this, right? 2 times node answer node dot answer. Yeah, because the values we store in this answer is a pair, right? But it asks us to return the total parentheses. That's why we need to do a 2 multiplied by 2 here. So so the queries, the first one is L and right, right? Since we're going to query it based on the current range, and then we're also gonna maintain the current S and E. The L and R is the node range, the current node range, and then the S and E is our query range, and then the index of the tree. So, okay, and so to query the range, right? I mean a few base cases we want to return first. Let's say the first case is that if the current range is completely within the range of the start and end, then we simply return the node because we know, okay, so this is the node we can return. Basically, if the S is smaller than the L and the R is smaller than the E. So this means that current node range is inside query range, right? Then we can return this node, return the tree of I, right? Remember the tree of I returns the node of the current node. And then the another case is that the if S is greater than R, right? If the star is greater than the right one, or the end is smaller than the left, then we return the node of 0, 0, 0. So this one is like current node range does not have any intersection with query range, right? And then if there's nothing to be intersected, right? Then we just return the empty node. Otherwise, right, we just again do a middle equals to the L dot R divided by 2. Then we have a LC. Actually, I can just copy paste this part here. Then we have a node of left node going to be the query of the L dot middle, and then start and E remains the same, and then the LC is the same. And then node of R right node is going to be the query middle plus 1. Then in this time it's R, but S and E is the same, and then RC. Here we return the merge of LN and RN. Yeah, that's how we do the query, right? And then yeah, I think we can just run the code here. Let's try to find this example here. So we need a 00210,466. Okay. Yeah, 00210,466. Yeah, cool. I think this one works. Yeah, I mean this is the it's a long implementation, and basically, we are basically we built the segment tree, ground up, and the key point for this problem is that we store 3 values in each node. The first one is the matched pairs for the current range. Second one is the unpaired left parentheses, and the third one is the unpaired right parentheses. Because when we try to update the parents, we need both the LP and the RP from both the left and right child to calculate the current parent's value. And after building this up, the rest is just like the regular segment tree query. Basically, we split this two to 5 into different segments until we have find like a completely coverage for the current node, and then we return that node, and then we do a same merge to that. Cool. I think, and after this one, sorry, so after this one, I think the time complexity is gonna be n to the, sorry, it's m times log n. Yeah, m times log n, because to build this segment tree, like since the maximum node is 4n, so to build this segment tree, we have 4n time complexity, and then to query, we have m times log n time complexity. Cool. I think I'll stop here. Thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.